Hello, everyone. Welcome to my webinar. Today, I'm going to be talking to you about how you can reduce your storage costs on ephemeral storage EC2 instances with Ondat. First, a few things about me. My name is Angelos Perivolaropoulos. I am a product reliability engineer, and I work. I think my screen stopped sharing. Yeah, I think we're back now. Let's start again. First, a few things about me. My name is Angelos Perivolaropoulos. I'm a product reliability engineer at Ondat, and I work in the PRE team. And as part of my work, making sure that Ondat is reliable, I'm daily working with Kubernetes clusters, and most of them are on AWS. Recently, I've been experimenting a lot with using Ondat in different types of EC2 instances, including ephemeral storage EC2 instances. And today, I'm here to show you my results on those findings. First, let's talk a little bit about Kubernetes. Everybody knows that Kubernetes works great with stateless applications. Pods can go up and down without causing much impact, and you can have node failovers that are automatically resolved without any downtime, since, again, the pods can leave one node and go to another node very easily. Well, to be honest, the truth is there's no such thing as stateless architecture. It's just always someone else's problem. Like, for example, stateless applications actually do have state. For example, a web server does have to store the session somewhere, which is usually in memory. So if it goes down, you lose those sessions, which means that either you have to recover by using your user's cookies, or have them restart the session all over again. So in essence, stateless is not something that doesn't have state, but it's something that can recover its state very easily from scratch. And you might ask then, there are some other applications that obviously can't recover those states from scratch. Stuff like databases. If a database loses its state, it can never really get it back from scratch. And this we call stateful applications. And in the same way that stateless applications, it's someone else's problem, for stateful applications, we want Ondat to be the solution to your problem. So let's talk about how Ondat is able to solve this issue. A few things about Ondat. Here you have a diagram about the Kubernetes cluster. It has a control plane, and it has 3 worker nodes. What Ondat does is it provides storage to your stateful applications that you have spun up into that cluster by creating a persistent volume in the data mesh, and also a replica. So as you can see here, each worker node has an infrastructure with a backend disk, and Ondat is using that backend disk to create those volumes and replicas for those volumes. And those replicas are actually copies of the data of the original persistent volume, which we call a master. So if a worker node goes down, then that persistent volume is easily able to fail over to a new replica. And in the same way as stateless applications are able to easily recover the state, Ondat can recover the state of your application by failing it over to its replica, and it's like it hasn't failed over at all. An extra thing that Ondat does to make sure that your data is always available is by making sure that those replicas have topology-aware placement when they're getting created. So all these worker nodes are actually in different AZs, and the replicas and masters, and if you have another replica as well, it would make sure that they're all in different availability zones. Next, let's talk a little bit more about ephemeral storage EC2 instances. Ephemeral storage EC2 instances are a type of EC2 instance that are able to launch with temporary block storage. For example, M5DX large is one such type of instance. As you know, when you spin up an EC2 instance, it comes with an EBS attached root volume. The same thing happens with ephemeral storage EC2 instances. They have an EBS root volume, but in addition to that, they also have a temporary block level storage. So in this example, you can see that we have an instance spinning up and then getting assigned one ephemeral disk from this instance store that exists in the host computer of AWS. Now, what this means, because you no longer are dealing with network block devices, you're dealing with local lock devices, it means that those block devices have way, way higher IOPS than network ones. You don't have to go through the network to connect with it. You can do everything in the same machine, which is very, very useful. But there is a downside. If those instances get terminated, then your data is lost. The block device gets detached and cleaned up and getting back to the instance store. And thankfully, Ondat is here to ensure that this is not actually a big issue. If your instance get terminated, as I showed you earlier, very simply, you have another copy of it that you can easily move your application over and be using that instead. And then another replica is getting created. Okay, that's great. We have very fast block storage with those EC2 instances, but how much faster is that actually? So I have this graph that I'm going to show you, which is comparing it with EBS GP2. Both are 150 gigabyte block devices. One is EBS, and the other one is from an Ephemeral instance. In that test, you can see I'm using a 2 gigabyte FIO test, which is straight to disk. So this is not using Ondat in this case. This is just a straight to disk FIO test that I run on two machines that both have 150 gigabytes of 150 gigabytes block storage. And you can see that Ephemeral is around 55K IOPS, while the 150 gigabyte EBS GP2 volume is only 3,000. And the same for writes, 3,000 for EBS, and it's around 30,000 for Ephemeral. And you can see this is a huge difference, which we would expect because we're comparing an SSD to a network block storage. And always the SSD is going to win. Let's have a look at the full results in this case. I have a table here. These results also are being run in a 4 vCPU, 16 gigabyte RAM machine, which is an M5X large and an M5DX large. Just those are the two EC2 instances I've been comparing because they're most equivalent. And I have here different results for straight-to-disk Ephemeral, straight-to-disk EBS, no replication Ephemeral. This is using Ondat this time with no replication EBS, and then again using Ondat, but this time with replication. And you see some very, very interesting results. These are the results I showed you earlier in that graph. We can see again the huge difference. But then when we move to using Ondat, you can see that this difference is actually much smaller. It looks like it's even actually higher than the straight-to-disk Ephemeral. This is because Ondat uses caches very intelligently and has a lot of very smart ways of making sure that you get as much performance as you can from your volumes. And in this case, it goes even higher than the random IOPS. This is obviously like the best case scenario. This is a benchmark where only this is running in a cluster. The real numbers, if you run the cluster, are going to be lower, but still you can see that Ondat is trying to squeeze out as much performance as it can from your volumes. Then we can move on into bandwidth, and then we'll see another curious result. The actual bandwidth of the straight-to-disk Ephemeral is quite comparable to the straight-to-disk EBS. And the reason is that AWS is actually putting a cap on the bandwidth of your storage, unless you actually pay them for more expensive volumes. But in this case, this cap also unfortunately applies with Ephemeral EC2 instance storage. And depending on how big those instances are, the higher this cap is. In this case, unfortunately, it's 216 megabytes per second. But again, Ondat is coming to the rescue by allowing us to go even higher than that, intelligently using caches. Another thing we can see the latency is actually much, much lower, about a tenth lower compared to EBS. And again, for the bandwidth of sequencer in the write, it's not that big of a difference. And again, a big difference for mixed random read and writes. So this is a benchmark that randomly tests sometimes read, sometimes write at random intervals. Okay, this is a 2 gigabyte file FIO, which means that it's very easy to save that to memory. So let's try similar benchmarks, but with a much bigger file. The same benchmark with a 50 gigabyte FIO file. You can see the results makes a bit more sense. Again, no replication Ephemeral, 51K IOPS, 27K for read, which is very close to how it was for random read and write, straight to disk. And for EBS, this time we can see that you can't really cache reads for such a big file, but thankfully you can actually cache writes. So we're able to be much faster on having much faster IO on writes. But again, for the bigger this file is, this advantage is going to slow down, and the more stuff you have on the cluster, this advantage is going to become less. But you can still again see how Ondat is trying to make your volumes as fast as they can be in the situation they're at. Unfortunately, for latency, we see the same issue because, again, this can be in cache. You can see that the latency is, again, 1/10 with EBS. So to me, it looks like it's a clear-cut case that ephemeral storage is much faster than EBS. So you'd assume it properly, you'd have to pay way more money for this. But the reality is, it's not that much more money. So let's see how much it would cost to have an M5X large GP2 with an M5X large instance with a GP2 EBS volume. Just the instance itself would cost $162 per month, and the 150 gigabyte GP2 EBS volume is $17 per month, which equates to $179. On the other side, if you want to use an ephemeral storage one, you'd have $191, and that's it. You don't need any more, because you don't have to attach any more network block device into this. But let's say you actually want to use something like EBS, you want to use EBS and have the same performance. Well, unfortunately, then in this case, you have to pay up, and you have to pay up a lot. If you want to have 55K IOPS with for an 150 gigabyte IO2 EBS volume, that's $3,651 a month. And as you can see, the difference is monumental. It's a very big difference. And to put in perspective, it's 95% less. And not only that, you're actually seeing even more improvements compared to using GP2 instances. In this case, you can see that the burst balance is a thing that is a drawback of GP2 instances, where in my testing, I ran my benchmarks for 3 days straight. And around the first day mark, you can see that the burst balance went to 0, because my credit went to 0 after using for a while, which for 150 gigabyte volumes, the minimum of IOPS is actually 0. So my volumes just stopped working after 1 day of very, very heavy use. Ephemeral storage EC2 instances don't have that issue. And now again, you might ask, okay, but is that reliable? We're talking about ephemeral storage. The reality is that how often would it happen that you'd have an instance terminate on you? And if you're using Ondat, your data is being stored into 3 different copies. If you're using 2 replicas, for example, for you to be able to lose your data, you need 3 instances in 3 different availability zones to get terminated at the same time, which is a very unlikely scenario. Now, if you ask me, would I have my nuclear launch codes saved onto this? Probably not. But for 99.9% of use cases, it is reliable enough to be able to be used. And what kind of applications would you actually use it for? As you saw, as we saw from the graph earlier, you can see that while the IOPS are very high, the bandwidth is about the same as EBS. And also the latency is much lower. So if you have an application that is reliant a lot on high IOPS and low latency, then you'd like a database, for example, this would be a perfect use case for it. But if you want something like Kafka that needs a lot of bandwidth, then this might not be the right use case for this. But you'd still get very comparable results to EBS. Okay, that's great. So let's actually show you how you can use this technology yourself with a demo. So let me show you what I have here. I have a Kubernetes cluster with 5 nodes, which I've just created. And if I actually look at what those nodes are, there's 2 of them that are in EU West 1, EU West 2A, one of them in EU West 2B, and one of them in EU West 2C. They're all using M5. Let me actually show them to you on the console as well. They're all using M5DX large instance types, and these are the name of them, and they have one master. So all of these workers are already joined in the cluster. And if I SSH into one of them, you can see that in addition to the normal root disk, the normal root mount point, they also have the NVMe 1N1, which is 140. It's supposed to be 150, but AWS actually gives you 140. And this is what we're going to be using to install Ondat on. How do we do this? Well, it's quite simple. We have to run the following commands. First, we need to actually do a makefs. So this will format the partition into ext4. That's done. Then we need to create a varlib storage OS directory. This directory is used, and we're going to have to mount it to our new partition. Oh, sorry about that. And now, as you can see, it's mounted. The reason we're doing this is because the way Ondat works is that it's going to try to use this specific directory, and whatever is mounted there is the device that it's going to be using. By default, it's going to use the root file system. But in this case, if we have something else mounted, it's going to be using the ephemeral storage EC2 block device. Okay, that's great. Now we have set up. This is for, I've shown you how to do this for one node, but I've already done it the rest of the nodes. I just want to show you as an example. So now our cluster is ready to have Ondat installed on. How do you install Ondat? It's a very simple process. If you go to our documentation and you go to install, and you go to Kubernetes, you can see that you'd need to use the StorageOS kubectl plugin, which you can install with just this command. I have already installed this on my cluster. I don't need to install it again. One of the requirements that we're going to be using now, if I show you the command I'm going to be running, kubectl StorageOS install, and then we're going to include etcd, and we're going to be using the etcd namespace StorageOS and the STOS version 2.6. And I have another version of this command here to show you. And we also have to use a specific storage class. By default, it will use your default storage class. If you don't have a storage class in your machine, for example, in most cases, you probably would have an EBS storage class to use. If you don't, you can use the local path provisioner, which I'm going to be using in this example. After you have a storage class installed there, this storage class is going to be used by etcd. Ondat is using etcd to keep a hold of its state. So if I have added the command of include etcd, the etcd is going to be installed along with Ondat. So let me run this command and show you. This might take a bit of time to install. This takes around 3 minutes most of the times. So while this is getting installed, I'm going to show you. You can see here the namespace is getting configured. I'm going to show you what the next steps are. The next step is I'm going to show you how this failover works in action. By doing this, I'm going to be creating a MySQL. I'm going to be creating a MySQL app, which you can see the stateful set here. This is just a standard stateful set that creates a MySQL pod, and it's using the storage class replicated. And this storage class replicated, what's special about it is that if I open it up for you, you can see that it's using the StorageOS topology aware label. This will make sure that the replicas of this of the storage class are always going to be in different availability zones. So let's see, has the cluster actually gotten created? Still in initializing state. So I'm going to be talking to you a little bit more about how that works. As I showed you earlier, this is checking the labels of failure domain .beta.kubernetes IO zone EU West. So depending on what zone this is, it's using it as the identifier for which availability zone this node lives in. This can be a custom label if you want to be with if you're not on AWS, if you're running this on something else, or if you're for some reason this label is used for something else, you can select your own custom label. But in this scenario, we're just going to use a default label that shows which availability zone this node is in. Now let's see, has Ondat been spun up? Yeah, we can see that Ondat is there. So next step is to apply the storage class. We can see that the storage class is there, it's been created. So let's create our MySQL application. You can see that PVC is created and is bound for the storage class replicated. And the MySQL application is also getting created. It should take a few seconds. We can watch it while we're waiting, and it's done. Awesome. So let's add some data into that MySQL. So let's create a database called shop. Let's use this database. And let's create a table. We'll call books. And in the table, let's insert a book. That's called Gates of Fire. Now let's see that the book is there. So the book is there. So let's find a little more information about this volume before we go to the next step. Before I do this, I'm gonna apply this storage CLI. What the CLI is, usually you can use a storage CLI from your machine, but for the sake of this demo, I'm using it as a pod inside the cluster. And this will allow us to get a bit more information about the cluster. So let's look at it being spun up. I think it's already there. Yep, you can see it here. So I'm gonna exec into that pod, and I'm gonna run storage get volumes. That's A. This will show us all the storage volumes in the cluster. And then if I do a YAML, we can find more information about them. Like in this case, we can find out where its master is and where its replica is, which will be great for our failover test, because now let's see how it will happen if in an ephemeral storage EC2 instance, we bring it down. What will Ondat do in this case? So we can see that the master is in this node. If we look at it here, let me find again the name of it. It's 1074.30.161. And if we look at which node that is, 161, it is in zone 2A. And then for the replica, 58, it is in zone 2C. So let's see what happens if we actually delete the one that's on zone 2A. Let's see which one that is. It was 161. This one, it's not this one. Oh, sorry about that. $161 is this one. So let's kill it and see what happens. So while this is shutting down, now this is not working because we managed to hit the one where the CLI was on. So you can see that it failed over to the new replica, but it didn't manage to find another replica to recreate it, which is normal in this case. Let's see what happens to the node, to the pod. Oh, I forgot to drain it. So that's going to take a little bit longer to spin up. Okay, I skipped the step of actually draining the the node, unfortunately, which means that it'll take some time for the Kubernetes to be able to understand that the pod was gone. So I was prepared for a scenario like this. So I have another cluster where I've already done this. And you can see that I've repeated the exact same scenario. And you can see here that when I do shop, oh, sorry. You can see that the title is still there, even though we have deleted the volume, the node. The data is able to move to the new replica and still keep all the data despite the failover. Now, if you wanted to try those benchmarks and all what I'm showing you right now yourself, you can go to our use cases page, and the use case I'm using is just a simple MySQL use case. And the benchmark I've been doing are just the simple dbench benchmark that you can run yourself by cloning this and creating the dbench.yaml job. If you want to make it even easier, you can go to our self-evaluation guide, where we have a section for benchmarks, which is at the bottom, so benchmarking. And you can test stuff yourself by just running this curl command. Thank you, everyone. Do you have any questions on this?
Hi, so we have a few questions. Give me 2 seconds. So we have, if an ephemeral storage instance gets rebooted, does the data get lost?
So the data only gets lost when the instance is terminated. So you can reboot instances without any issues to your data.
Okay. And then there's another question that's just come in. What applications work best with ephemeral storage instances?
So as I mentioned earlier, databases are a very good use case for this. So things that want very high IOPS and low latency, but not necessarily high bandwidth. These are the kind of application that works best for this.
Okay. Another one's just come in. What happens if I lose 2 availability zones?
Assuming if you lose 2 availability zones, most likely that means your Kubernetes CD is probably going to have problems. But assuming that you have a way around this, if you're using two or more replicas for your Ondat applications, then you shouldn't have any problems because you still have one copy of the data. As long as there is one copy of the data still in the cluster, your data is still going to be there.
Cool. And one last one. Do all ephemeral storage EC2 instances have high IOPS?
So that's one thing you should be careful about. If not all of them are using SSDs, some of them are using hard drives. So you need to make sure if you're using ephemeral EC2 instances that you choose the ones that use SSDs instead.
Cool. I think for now those are all the questions. Thank you, Angelos.
Thank you. If you want to use Ondat now yourself, we have just spinned up a new SaaS platform along with our version 2.6 release that you can very easily click here and you can sign up. You can also request a demo if you want to speak to sales for us. You can use a Google account or a GitHub account to sign up. And another thing is that we're hiring. Ondat is a really great company to be working at. I would highly recommend them. We have a lot of fun there. I'm having the freedom to be able to experiment and try stuff like that. So if you are interested, you can go to ondat.io/company, and perhaps you could even join us. So that's it from me for today. Thank you, everyone, and thank you for joining my webinar.